Hello, welcome back to AC Circuit Analysis. We're doing Delta-Wye circuit problems. This is problem number 3, and this is going to be what I really consider to be our first really full-blown problem that has a delta source and a Y load. So what we have again is a wall of text that we need to decipher, but the process is going to be the same. We're going to decipher what we have in this problem. We're going to draw a picture, and then we're going to step-by-step inch our way forward through it. Now what you need to realize is that since now we have already done all of the YY problems in the past, and we've introduced and done some kind of simpler problems with the delta source, right? Now we're putting it all together, so some of this problem is going to be dealing with the delta source, some of it's going to be dealing with the load end of the problem. So the stuff that you've learned in the past is all going to be brought to bear because we're going to be doing things like voltage conversions in the way that we've done them in past problems. We're also going to be doing current conversions as we've been doing them here in the delta sources. I guess what I'm trying to say is that now we're to the point where we're putting pieces together from different parts of the course. So some of the parts of this problem will look like things we've done before because they are things that we've done before, while we'll have some new pieces in the delta source part of things that we've been talking about here. So enough talking, let's get to it. We have a balanced negative sequence circuit. It's a delta source, and it has an impedance of 0.018 plus J 0.162 ohms per phase. So this is all talking about the source. So the delta source is a delta balanced negative sequence source, and the source impedance is what's given by this in each leg of that delta. And then it says at no load, we'll talk about that in a second, at no load, the terminal voltage of the source is 600 volts. Okay, so that's a piece of information. Then we talk about the line impedance that this source is connected to. It has an impedance given here, 0.074 plus J 0.296 ohms per phase, so that's talking about the line. And then that line is connected to a Y load. So you see it's a delta source and a Y load, and the Y load has an impedance as given by this. Notice the line impedance is an inductive impedance because we have the positive J, but the Y load has actually a capacitive impedance because we have minus signs. So we have a real and imaginary part, so resistive and capacitive part of the load. So we have 5 things we want to do. The first thing we want to do is what we always want to do anyway, usually, and that's to draw a single phase equivalent circuit, but it says that it wants you to use VAB prime as the reference. I'm going to get back into what that means a little bit more in a second, but basically we're drawing a single phase equivalent circuit, and when you're using something as a reference, it means that you want to use that as your 0-degree phase. When you see some problem that says use this as a reference, it just means it's code for take that to be 0 degrees phase, and everything else, every other phase angle in the circuit is just going to be relative to that reference, which is 0 degrees. Part B, after we've written the single phase equivalent circuit down, we're going to find the magnitude of the line voltage at the load. So we have like VAB, for instance, but we're only asked to find the magnitude, and we're asked to find that magnitude of that line-to-line voltage at the load. Next, we're going to find the 3 line currents. It's not too big of a surprise, AA, BB, and CC. So once we find one, we'll find the other 2 by adding, subtracting 120. And then we'll find the phase currents in the source. Phase currents, remember there's a triangle. The delta source is a physical triangle, right? So we want to find the phase currents, which are circulating, I shouldn't say circulating, but they're present in these 3 legs of that triangle. And we have them labeled here. I, BA, CB, and AC. And if you remember, we talked about this in the last section and also previously. In a delta source, the subscripts here for the currents that are circulating around that triangle are flipped around. So usually, like for a load, it's AB, BC, CA, goes like the alphabet. But on the source side of the circuit, we flip these subscripts around. So for the A phase, instead of AB, we're trying to find BA. Instead of BC, we find CB, and instead of CA, we find AC. So basically, we're just flipping the subscripts around, and that comes about because this is a source, so the current has to be leaving the power supplies, and we'll draw a picture and you'll see in a second. But that's why these subscripts are backwards from what you might expect there. And then the last thing is to find the magnitude of the line voltage at the source terminals, the magnitude of the line voltage at the source terminals. All right, so the first thing we want to do is draw this single phase equivalent circuit. And you're always going to start by drawing them basically the same sort of way. So you have to draw a triangle, and in each leg of this triangle, we're going to have a resistive part and an inductive part, and then we're going to have some kind of source in each leg of the triangle. So let me quickly draw this guy. So I'll have an inductor here, resistor here, we'll have some kind of source here. Here we'll have some source here, then we'll have resistive part, inductive part, and then we'll kind of close our triangle off like this. Okay, and then what we will do is we'll have plus minus here, plus minus here, and then plus minus here, and you can